On March 8, 1892, at 4:37 a.m., civil engineer Joseph Bazalgette watched as his team attempted what 7 other engineering firms had deemed impossible. Knee-deep in mud beneath London's Fleet Street, the tunnel was slowly collapsing. Again, 43 feet below street level, in soil that shifted like wet sand, Bazalgette's experimental brick arch was cracking under pressure that, according to all his calculations, it shouldn't have been able to withstand. He was 47 years old, had built sewers on 3 continents, and had never failed in any of his projects until now. The city council had given him 11 months to complete the 2.3-mile-long main sewer line through London's most unstable geology. 5 months had passed, and he had advanced 200 feet. At this rate, it would take 4 years to finish. The council would terminate the contract in 6 months. Bazalgette had one last idea. This idea defied all the principles of Victorian engineering. It required materials that did not officially exist, and if it failed, the tunnel would flood and kill everyone inside. This is the story of how an engineer rewrote the rules of construction to save a city drowning in its own waste. If you like stories like this, subscribe and don't forget to like. London in 1891 smelled like death. Literally. The Thames was an open sewer. Cholera killed 14,000 people that year. The old medieval waste system couldn't handle a population that had grown from 1 million to 5.6 million in 60 years. The government commissioned a new deep-level sewer network, 14 miles of tunnels, some running 60 feet below street level, designed to carry waste downstream to treatment facilities beyond the city. Simple concept, impossible execution. The problem was the soil. London sat on layers of clay, sand, and gravel that shifted unpredictably. The water table fluctuated daily with Thames tides. Traditional mining techniques didn't work because the tunnels were too shallow, hitting water at 15 feet depth. Traditional cut-and-cover methods didn't work because Fleet Street was the city's busiest commercial corridor. You couldn't tear up the street for 4 years. The engineering firms that bid on the project all proposed the same solution: brick-lined tunnels using the arch compression method that had worked since Roman times. All 7 firms quit within 6 months. The brick arches collapsed, the tunnels flooded, men died. Bazalgette took the contract in October 1891 because he was desperate. His firm was failing. The cholera epidemic had killed his daughter 3 years earlier. He wanted revenge on the disease, on the filth, on the incompetent city planners who'd let London decay into a cesspool. The council offered him £47,000 for completion, £4,000 for every month of delay past November 1892. 11 months. He'd never built anything that fast. Nobody had. His first innovation was speed. Traditional bricklaying required mortar curing time, 24 hours between courses. Bazalgette used a quickset hydraulic cement formula from Portland that set in 4 hours. His crews worked in 3 shifts, one laying brick, one preparing the next section, one shore propping behind. They moved like an assembly line. The tunnel advanced 12 feet per day, fast enough to meet deadline, until they hit the Fleet Street substrate. The soil beneath Fleet Street was saturated clay, mixed with pockets of quicksand. Every engineering textbook said the same thing: don't tunnel here. The lateral pressure from surrounding soil was too high. The vertical load from buildings above was too heavy. Any tunnel would collapse within weeks. Bazalgette knew this. He tunneled anyway. His first arch collapsed on November 3, 1891. Ispacton Pleedmal, its Buckstreet Dinker Remiswa. Its Bacter ended Sahem A, the Breach Tunnen. With bound Bordelia had a fears. Fuel saw morg prim for a gene. With bowed the paired 7 and tracks. went out Thames to Roll Street. Bazalgette attended the funeral, listened to Whitmore's widow say she needed the compensation money to feed 3 children, went back to the tunnel that night and calculated a different approach. The problem was the arch itself. Roman architecture used compression, each brick pushing against its neighbors, the load distributed evenly through the curve. Beautiful mathematics. Worked perfectly in stable soil. In unstable soil, the arch needed external support, but there was no external support, 43 feet underground. Bazalgette couldn't build buttresses. There was no room. He needed the arch to support itself without relying on the surrounding earth. That required a structural principle that didn't exist in 1891. Tension reinforcement. Bazalgette had seen American engineers using iron rebar in concrete foundations, a new technique from Chicago. The iron absorbed tensile stress that concrete alone couldn't handle. What if he applied the same principle to brick? What if he embedded iron bands inside the mortar joints, creating a cage that held the arch together, even when external pressure tried to push it apart? The mathematics worked. The materials didn't. Iron rebar wasn't manufactured in England. Importing from America would take 3 months. He had 6 months left on contract. He found the solution in a shipyard. Decommissioned naval vessels were being scrapped at Deptford. The ships had iron reinforcement bands around their wooden hulls, curved sections, preformed, designed to resist lateral pressure from seawater. Bazalgette bought 340 tons of scrap hull banding for £800. He cut the bands into 8-foot sections, drilled bolt holes every 6 inches, and created a lattice framework that wrapped around the inside of his brick arch. Each iron band was embedded in mortar, bolted to its neighbors, forming a continuous tension cage inside the compression structure. The hybrid design was insane. Victorian engineers didn't mix materials. Stone was stone, brick was brick, iron was iron. You didn't combine them because expansion rates were different. When temperature changed, the materials moved at different speeds, creating stress fractures. Bazalgette didn't care about Victorian engineering principles. He cared about finishing before the deadline. He tested the design on December 15, 1891, in a section beneath Ludgate Circus. The soil there was the worst, pure saturated clay, 8 feet of lateral pressure per square foot. His crew built a 30-foot section using the iron-banded arch method. Then they waited. Traditional arches collapsed within 72 hours in this soil. Bazalgette's arch held for a week, 2 weeks, a month. On January 18, 1892, he ordered full production. Every tunnel section from that point forward used the hybrid design. The work was brutal. The tunnel was 7 feet high, 6 feet wide. Men worked in darkness except for oil lamps that burned oxygen and filled the air with smoke. The temperature was 38 degrees Fahrenheit year-round. The smell was sewage, Thames water, human waste seeping through soil. Shifts ran 12 hours. Men entered at dawn, emerged at dusk. Some didn't emerge. On February 9th, a gas pocket ignited. 3 men suffered burns. On March 3rd, a water main broke above the tunnel. 15 men evacuated as 4,000 gallons flooded the section. On April 11th, a brick hoist cable snapped, dropping 2 tons of material that nearly killed the entire morning crew. Bazalgette was underground for every incident. He didn't manage from an office. He wore the same mud-covered work clothes as his laborers, carried the same oil lamp, breathed the same toxic air. When men refused to enter a collapsed section on April 28th because they thought it was cursed, Bazalgette entered first, alone, spent 2 hours checking the structure, then emerged and told the crew it was safe. They followed him back down, not because they believed the tunnel was safe, because they believed Bazalgette wouldn't waste their lives. By June 1892, they'd completed 1.4 miles, Ahead of schedule, the council sent inspectors who couldn't believe the iron-reinforced design was stable. They demanded stress testing. Bazalgette agreed. On June 14th, they loaded a completed section with 40 tons of sandbags, double the expected waste flow capacity. The arch held. The inspectors approved continuation. The council extended funding. The final challenge was the Thames crossing. The tunnel had to pass 52 feet beneath the river, through soil that was 60% water. Every engineer said it was suicide. The water pressure at that depth would burst any tunnel. Bazalgette's solution was elegant. He didn't fight the water. He used it. He designed a sealed caisson system, a watertight iron chamber that sat on the riverbed while workers excavated beneath it, building the tunnel in a dry environment. The caisson was then lifted and moved forward. The technique had been used for bridge foundations, but never for tunnel construction. The Thames crossing took 7 weeks. They worked in shifts around the clock. The caisson leaked constantly. Pumps ran 24 hours a day. On August 3rd, a pump failed. The chamber flooded in 90 seconds. 17 men were trapped. Bazalgette was on the surface. He could hear them pounding on the iron walls. He had 2 choices: open the chamber and flood the entire tunnel section, killing everyone but possibly saving the 17, or seal the chamber and hope the backup pump engaged before they drowned. He chose the backup pump. It engaged 4 minutes later. All 17 men survived. 4 of them never went back underground. Bazalgette didn't blame them. On September 27, 1892, the final section was completed. Total length, 2.34 miles. Total time, 11 months, 19 days. Under deadline by 11 days. The council paid the full contract plus a £2,000 bonus. The sewer system operated perfectly. Cholera deaths in central London dropped from 14,000 in 1891 to 320 in 1893. The system still operates today, 133 years later, carrying waste for 9 million people. But Bazalgette's real innovation wasn't the sewer. It was the construction method. His iron-reinforced brick arches became standard practice in underground construction worldwide. The caisson technique for underwater tunneling was adopted by New York's subway system in 1904. The rapid cure cement formula was refined into modern quickset concrete. The shift rotation system for tunnel crews became industry standard. One project, 11 months, changed how humanity built underground infrastructure. Bazalgette never built another sewer. The cholera epidemic ended. The demand disappeared. He returned to railway engineering. Died in 1906 at age 61. His obituary in the Times mentioned his railway work, his service to the city, his contributions to public health. One paragraph mentioned the Fleet Street sewer project. It didn't mention the iron reinforcement, the hybrid arch design, or the fact that he'd invented techniques that would be used for the next century. The engineering community knew. They'd been using his methods for 14 years by the time he died. But the public didn't care about sewers. They cared that the city didn't smell like death anymore, that cholera didn't kill their children, that the Thames was clean enough to fish in again. The Fleet Street sewer is still there, 52 feet below the pavement, carrying waste in silence. Modern engineers who inspect it are always surprised by the iron reinforcement bands, the precision of the brick arches, the quality of construction that's outlasted everything built above it. They ask how Victorian engineers achieved such durability without modern materials. The answer is simple. One man refused to accept that something was impossible, rebuilt the rules when the old ones didn't work, and proved that unbuildable just means nobody's solved it yet. If this story moved you, please like and subscribe. Tell us in the comments where you're watching from.